Number 1, it says a chemical bond is formed when electrons are, and specifically we want to make sure that we know that these are valence electrons. Okay, these are the only electrons that are involved in chemical reactions. Okay, are just the valence electrons, nothing else are involved in it. Okay, and the choices are lost, shared, gained, or all of these. Now when we're looking at this, anytime that valence electrons is lost or gained, we know that this is an ionic bond. Okay, so in a chemical bond we do have ionic bonds, and they are lost and gained in those. If we have shared, we know that we have a covalent bond. Okay, this is when the electrons are shared between both of the elements. Okay, so the correct answer on number 1 would be all of these, because if they're lost or gained, it's ionic. If it's shared, it's covalent, and all of those are chemical bonds. Alright guys, moving on to number 3, it says which of the following compounds has an ionic bond? Okay, the two bonds that we mainly deal with are ionic and covalent. Ionic is always between a metal plus a nonmetal, and a covalent bond is always between a nonmetal plus a nonmetal. Okay, remember ionic, you have the transferring of electrons, or the giving and taking of electrons, and in covalent you have the sharing. So when we're looking at these compounds, the first thing you have to do is the first element within an ionic compound has to be a metal. So all we have to do is look at the very first element and see, was it a metal or is it a nonmetal? Okay, and if it's a metal, then we know it's ionic. Now remember that metals are located to the left of the stair step on the periodic table, and nonmetals are located to the right. So we look here, and the first one we see is hydrogen, and in this case hydrogen is one of the exceptions. Hydrogen is always considered a nonmetal. So in this bond right here, we know that it's going to be an acid for us, so we know that this is not ionic. Carbon is a definite nonmetal, so we know that that's covalent, and then we have our sulfur, which is a nonmetal, so that is going to be covalent. So the correct answer should be is number 2, because sodium is definitely a metal, and as we have sodium chloride, it's a metal, or it's an ionic bond because we have a metal plus a nonmetal. Okay guys, go ahead and move on to number 5. Now it says use electron dot notation to demonstrate the formation of ionic compounds involving lithium and chlorine. So we know that we have an ionic bond, an ionic compound, because it's between a metal, which is lithium, and a nonmetal, which is chlorine. Now the first thing that we have to do here is we want to crisscross. Anytime we have an ionic bond, to write the formula for it, we've got to crisscross. To crisscross, what we always crisscross is the oxidation numbers. Okay, and to remember the oxidation numbers, we always use our hill of oxidation numbers. Okay, we know that group 1 has a +1 oxidation number. Group 2 has a +2 oxidation number. We switch on over to 13, and it's going to have a +3 oxidation number. 14 has a plus or -4, depending on if it's a metal or a non-metal. Remember, that's looking on the stair step. 15, we know that we're going to have a -3. 16, we're going to have a -2. And 17, we're going to have a -1. Now remember that group 18 is not on here because 18 is noble gases. They do not have an oxidation number because they don't react with anything. So the first thing we got to do is figure out what groups lithium and chlorine are in. Okay, well lithium is in group number 1. So it's going to have a +1 oxidation number. So we have lithium with a +1, and then we have chlorine. We look and we see that chlorine is in group 17, so it has a -1 oxidation number. So all we do is we go ahead and we crisscross, okay, and we bring the 1s down. Now we don't really worry about the charges. What the charges tell us are where the electrons are going. Okay, lithium is positive, so it's going to be giving an electron to chlorine, and chlorine is negative because it received an electron from lithium. Okay, so our formula, the first thing we look for is we got to have a formula of LiCl. Now, what it looks like in electron dot notation is we have lithium, okay, which has 1 dot because it has 1 valence electrons. Remember that valence electrons are not oxidation numbers. Okay, we know that group 1 has 1 valence electron, group 2 has 2, 13 has 3, 14 has 4, 15 has 5, 16 has 6, and 17 has 7. Okay, and 18 has 8. The oxidation numbers are different than valence electrons. And lithium just has 1 valence electron. And then we look at chlorine, and chlorine's in group 17, so it has 7. So when we write it out, it's 1, 2, 3, 4, 5, 6, 7. And what actually happens is that this lithium will give 1 because chlorine, it has 7 and it's trying to get 8 because 8 is stable. So it just takes 1 from lithium, and it had 7, but it takes 1 and now it has 8. So what we should see is we should see that 1 dot going here, and that's where we get our lithium, which has a +1 because it gave it up, and then chlorine, which has now 8 valence electrons, would be -1 because it stole 1 from lithium. So this is what we should be looking for in our answer. Okay, moving on to number 7, it says use the electron dot notation to demonstrate the formation of an ionic compound involving the elements. We have calcium and we have iodine. Okay, so remember the first thing we have to do is we have to crisscross, and we got to get their oxidation numbers. Well, calcium is in group 2, so we know that's going to have a +2 oxidation number. Iodine is in group 17, so it's a -1 oxidation number. So when we crisscross these guys, we get Ca1I2. We're just written Cai2 because we don't have to write the 1. So this is the formula that we're looking for. And what we should see is we have 1 calcium, which has 2 valence electrons. And what it's reacting and doing is we see that iodine's in group 17, so it has 7 valence electrons. And we have 2 iodines because we have a 2 right there. And remember, they can only have 8. They want 8, but they can't have more than 8. So what happens is 1 of our valence electrons from calcium goes to that iodine, and another one goes to that iodine. And so that now both of the iodines have 8, and calcium's given up all of its valence electrons, so it's happy. Iodine's happy. So this is our electron dot that we're looking for, and this is our formula. Okay, moving on to number 9. Now in number 9 it says name the compound, and we have PbCl2. Okay, when we're looking at this, the first thing we have to do is figure out if it's ionic, covalent, or if it's an acid, because that depends on how we're going to name it. Okay, we see that it starts with Pb, which is lead, so we know that that's a metal, so therefore anything that starts with a metal, we know it's going to be ionic. So it's going to be an ionic compound. So we're going to use the rules for naming ionic compounds. And what we do is we just name the metal. Since this is lead, we don't do anything to change it, we just say lead. And then chlorine we change to chloride. Okay, but there's one extra step that we have to do. So we have our lead chloride here, but since lead is a D block metal, okay, since it's has more than one oxidation number, we have to figure out, well, is it lead 1 or is it lead 2 or is it lead 4? Okay, so the way we do this is we take our lead, our PbCl2, and remember that this 2 came from somewhere. Okay, basically what we're doing is we're doing reverse crisscross. Okay, since chlorine has a -1 oxidation number, we see that it matches, that 1 matches the subscript of the 1 down here, so this 2 has to be the oxidation number of lead. Okay, so because it came from up here. Okay, that 1 came from right there because chlorine has a -1 oxidation number, and lead would have a +2, which it brought it down right there. Okay, so here, since we have a 2, we would name this lead 2 chloride. Okay guys, moving on to number 11. It says, what is the formula for ammonium sulfate, which is formed from ammonium, which is NH4 ions, and sulfate, which is SO4 -2 ions. Okay, we have 2 polyatomic here. One thing I want you to remind you of is that on your periodic table, that's where you will find your polyatomics. Anything ending in 8 or ite is going to be a polyatomic. The one we have to look out for here is ammonium. It's a polyatomic. So we have to check and make sure they're listed out for us. So all you got to do is look on there, see if you can find them. And then we just treat this as a normal crisscross because this is a positive, which is a cation, and this is a negative, which is an anion. It's just basically what we have is we have a crisscross ionic compound. So what we would do is we take our NH4 and just put it in parentheses. Okay, keep our polyatomics in parentheses, and this would be a +1. Okay, and then we have our SO4, and we put that in parentheses, and that would be -2. So all we do is we crisscross their oxidation numbers, keeping everything in parentheses, and we have our NH4 2 SO4 1. And what we can do is we can get rid of that parentheses since it's an understood 1 out there, so we don't have to have it. So the correct answer would just be our NH4 2 SO4, which would be number 4. So with polyatomics, just make sure that we crisscross like a normal ionic compound, and we just put the polyatomics in parentheses and crisscross those. Okay, moving on to number 13, it says name the compound. Again, we have to figure out, is it ionic, covalent, or is it an acid? We see that it starts with potassium, and potassium is a metal because it's to the left of the stair step. So we're naming it using ionic rules, and all we do is we name it, and potassium, the metal stays the same, so it's just potassium. It's bonded to S, which is sulfur, which all we do is we change sulfur to sulfide, and we check and see if that metal is a D block. It's not, so this is just potassium sulfide, which the correct answer would be right here on number 1. So number 15, it says pick the name and formula that do not match. We see that all of these are acids, so we got to go over the rules for naming acids. Now there are two types of acids. There are binary acids and they're ternary acids. And when we're naming binary acids, what we're looking for is binary acids have the prefix hydro, and we put what it is, and then ic, and then acid. Okay. And if we look at this, we can look down here and we see that we have hydrofluoric acid. So to check and make sure that this one's right, we go ahead and we know that in a binary acid it's hydrogen bonded to one of the things. So this should be hydrogen bonded to fluorine. To check and see if the formula is right, we're just going to crisscross them. And remember, it's just like crisscrossing ionic bonds. We crisscross their oxidation numbers. So when we're looking at this, hydrogen's in group 1, so it'll have a +1 oxidation number. And then fluorine's in group 17, so it has a -1. So when we crisscross this, we get a 1 and a 1, which we see that that's the correct formula. So we know that number 4 can't be the right answer because it is correct, both in the name and the formula. Now, the other type of acid that we have is a ternary acid, okay, and that involves hydrogen bonded to a polyatomic. Now, if that polyatomic ends in ATE, like phosphate, nitrate, chlorate, anything like that, that ATE ending will change to IC and then acid. Okay, if that hydrogen is bonded to a polyatomic that ends in ITE, we know that that ITE is going to change to OUS and then acid. So if it was nitrite, it would be changed to nitrous, which if we look right here, we have nitrous acid. So since it ends in OUS, we know that this had to be ITE, which nitrite is hydrogen, nitrite is NO2. This has a -1. +1, we crisscross it and we get H and O2. So this can't be the correct answer because it's both of them are correct. Now oxalate, we look at this one, oxalic acid, and since it ends in IC, we know it had to be ATE, and oxalate is C2O4 with a -2. Bonded to our hydrogen, which is +1, we crisscross these, and that's where we get our H2C2O4, which that's correct right there. So we look at our very last one that we have, which is acetic acid, and since it ends in IC, it used to be ATE, which is acetate, which acetate is C2H3O2 with a -1 charge. So when we crisscross it with hydrogen, it's +1, -1. It's supposed to have a 1 down here. Okay, and we see that it has a 2, so that formula is not written correctly. So that the correct answer for this one would be number 1 because the formula does not match the name. Okay, go ahead and looking at number 17, it says pick the name and formula that do not match. Again, we see that we're dealing with acids, so we have to go ahead and take the name, write the formula. So when we look at this, we have nitric acid. It used to be nitrate, which hydrogen bonded to nitrate, NO3. This is +1. If we look on our chart, that's where we find all our polyatomics. We have our nitrate, which is -1. We crisscross those, and we get HNO3, which that's correct. So number 1 could not be the correct answer. We look at permanganate acid. Since it ends in IC, we know that it used to be permanganate, which permanganate is hydrogen bonded to MnO4, and it has a -1 charge, so +1 -1, and that's where we get our HMnO4. Here we see we have hypoiodous acid, which this used to be iodide, and so what we see here, hypoiodite, and that would be our this one's not on your chart, so I'm going to go ahead and tell you that this one is correct. It's just we would have our OI or IO with a -1 charge hydrogen with a +1. We crisscross these, and that's where we get the formula from. And then lastly, we have sulfurous acid. So it would be OUS used to be our ITE or sulfite, which that would be hydrogen bonded to SO3, which is a +1 -1. But we see that here, or sorry, +1 -2, which we crisscross those guys. But we see that they put an SO4. SO4 is actually sulfate, which it should have been sulfuric acid. So that one's wrong. So that would actually be the one that does not match. So number 4 is the correct answer. Okay, moving on to number 19, it says compounds which are characterized as covalent are generally made up of elements found on which part of the periodic table. Now, covalent compounds are made of nonmetal plus nonmetal bonding, and we know that nonmetals are found to the right of the stair step. So we know that it wouldn't be the lower left, it wouldn't be the upper left, it wouldn't be the left and the right. It is to the right of the stair step, which in that case is the upper right, which is going to be the correct answer. Okay, moving on to number 21. It says the best name for a compound we have N2O5 is. Now when we're looking at this, again, when we're naming, we have to know, is it ionic, covalent, or is it an acid? Okay, remember ionic is a metal plus a nonmetal. An acid starts with hydrogen, and so a covalent bond is between a nonmetal, and we see that that's what nitrogen's a nonmetal, oxygen's a nonmetal. So when we are naming covalent compounds, we use the Greek prefix system. That's the one where we have mono is 1, di is 2, tri is 3, mono, di, tri, tetra, penta, hexa, hepta, octa, nana, deca. And those go in order, so it's mono, di, tri, tetra, penta, hexa, hepta, octa, nana, deca, and that stands for which ones we have. So all we have to do is we look at the subscripts and we go ahead and we label them. Now we only label the first one if it's more than one. So we see that we have 2 nitrogens, so the Greek prefix for 2 would be di. So it's di-nitrogen. And then we have 5, which is penta, and oxygen. So in the second one, we always change the ending to IDE. So this is dinitrogen pentaoxide. So dinitrogen pentaoxide, which that correct answer would be number 4 on this one. Okay, moving on to number 23. What's the proper name for SO2? So we go ahead and look at it. It's a nonmetal bond, so we know that it's going to be covalent. So when we're looking at this, we know that we use the Greek prefix system. Now, since sulfur is the first element and it's by itself, we don't put mono with it. We just put sulfur. And we have 2 oxygens, so it's di, and we change oxygen to oxide. So this is just sulfur dioxide. Okay, moving on to number 25. It says the compound dinitrogen trioxide would have the chemical formula. So when we're doing this, all we have to do is di means 2, so 2 nitrogen. So we're looking down here, that one doesn't have 2, that one doesn't have 2 nitrogen, so we're down to this. And it's trioxide, tri means 3, so 3 oxygens. Dinitrogen trioxide, so it can't be this one because that has 5. So the correct answer would be number 3, dinitrogen trioxide. 2 nitrogens, 3 oxygens. Okay, moving on to number 27. It says ammonia can be prepared by the reaction of magnesium nitride with water. The products are ammonium and magnesium hydroxide. When the equation is written in balance, the coefficient of magnesium nitride is. So it's wants to know the coefficient. Now, anytime we have coefficients, we're going to write our chemical equation. And this becomes a little bit harder because we actually have to write out what the equation is. So when we're looking at this, it says that it's prepared by the reaction of its magnesium nitride with water. So when we're writing this out, we have magnesium nitride. Well, magnesium is a metal, nitrogen is a non-metal, so this is an ionic compound. So when we write this out, we have to crisscross. We have magnesium, and then we have nitrogen. Magnesium has a +2 oxidation number, and nitrogen has a -3 oxidation number. And we go ahead and we crisscross these guys, and we get Mg3N2. And it's reacting with water, which is H2O. Okay, and it tells us in the problem that the products are ammonia, which ammonia is a common compound. We have to know it's just NH3, and then magnesium hydroxide, which magnesium bonded to the polyatomic hydroxide, which is OH. So magnesium is going to be +2, hydroxide -1, which we find that on our formula chart, and we go ahead and we see that that would be our Mg parentheses OH 2. So when we're going ahead and we're working this out, now what we have to do is we have to balance it. So when we're going to go ahead and we're going to balance it, remember we have to have the same number of elements on each side. So the elements that we're dealing with are magnesium, nitrogen, hydrogen, and oxygen. Okay, and they have to be the same on the reactants and the product side. So over here we see that we have 3 magnesiums and we have 2 nitrogens. And then we have 2 hydrogens and 1 oxygen. Now on our product side, they have to have the same amount. So let's look at what we're starting with. We have 1 nitrogen, we have 3, 4, 5 hydrogens, and we have 1 magnesium, and we have our oxygen, that 2 distributes, and we have 2 oxygens. So we got to go ahead and we got to balance these guys out. So it doesn't really matter where we start. We save hydrogen and oxygen at the very end. So when we're going ahead and we're writing the coefficients for these guys, let's go ahead and start with our magnesiums. Okay, so our magnesiums, we're going to go ahead and we are going to put a 3, because it has a 3 here. We only have 1, so 3 times 1 is 3. But remember that that changes our oxygens as well. We have 2 because we distribute that 2 out. We have 2 times 3, which gives us a total of 6. And then it also messes with our hydrogen. 2 times 3 is 6 as well, plus the 3 that we already have, for a total of 9. Okay, so the next thing that we have to balance is, let's go ahead and balance our nitrogens. We have 2 over here, so we need 2 over here. So that distributes to nitrogen, which gives it 2, but it distributes to the hydrogen as well. And we have 2 times 3, which gives us 6, plus the 6 that we already have over here, which gives us a total of 12. So, and we see that our nitrogen went ahead and went to a 2. So everything's balanced except our hydrogen and our oxygen. So to come over here, we need 12 hydrogens. So we go ahead, we put a 6 right there, because 6 times 2 is 12. So now we have 12. It also affects the oxygens, and 1 times 6 is 6. So now everything's balanced. And our coefficients are going to be 1, 6, 2, and 3. Now it's asking us what is the coefficient of magnesium nitride. So on this one, we look at it. Magnesium nitride has a coefficient of 1, so 1 would be our correct answer. Okay, moving on to number 29. It says classify the reaction. Now the reactions that we have, We have a synthesis reaction, we have a decomposition reaction, we have a single replacement reaction, we have a double replacement reaction, and we have a combustion. Now, to classify these, to break them up as simply as possible, anytime we have a synthesis reaction, we have two compounds becoming one compound. In a decomposition reaction, we have one compound becoming two compounds, so it breaks up. It goes from one thing to two things. Here we go from two elements to one compound, so it becomes one thing. In a single replacement reaction, we have an element plus a compound, and what happens is it produces a different element plus a different compound. Basically what happens is the metals or nonmetals will switch places. In a double replacement reaction, we have a compound plus a compound, and it produces a compound plus a compound. And in a combustion reaction, what we have is we have hydrogen reacting with some type of, or oxygen reacting with some type of carbon compound. So we'll have O2 reacting with some type of carbon, and it produces H2O plus CO2. Okay, so in looking at this one, we see that we have our mercury 2 oxide, and we see that it goes from a single compound to two different elements, which is the classification of a decomposition reaction. Okay, on number 31 it says the chemical reaction. We see here we have an element plus an element, and it produces one single compound. It represents a synthesis reaction because we have two things becoming one thing. They're combination reaction, we could also call it that, but the correct answer would be synthesis reaction. Okay, moving on to number 33. It says the chemical reaction, and we see that we have an element plus a compound. Represents, and what we see in our product is we have a compound plus an element. And what we can see has happened is that this bismuth has come in there and knocked out our hydrogen, and basically they switch places. And now bismuth is bonded to oxygen and hydrogen is by itself. And this would classify as a single replacement reaction. Okay, moving on to number 35, it says what would the products for the reaction? We have bromine and potassium iodide. It just wants us to write the products of the reaction. Now the first thing we have to figure out is if the reaction is actually going to happen, and that's just determined by the activity series. Okay, in the activity series, what is by itself has to be above what it's trying to replace. So if what's by itself is on top, it will replace the like element in the compound. So in this case, we see that bromine is a nonmetal. Now, the nonmetal activity series is group 17, and fluorine, chlorine, bromine, and iodine. And it's just group 17. And nonmetals replace nonmetals, metals replace metals. So bromine is going to try to replace the compound or the element of iodine. So bromine has to be on top. So we look at the activity series, bromine is on top, so it can replace iodine. So what's going to happen is iodine is now going to be by itself, and potassium is now going to be bonded to bromine, so the correct answer would be number 4. One other thing I would point out is remember that we have to, when we have elements by itself, we have to check and make sure, are they a part of Brinkelhoff? Remember that Brinkelhoff represents bromine, iodine, chlorine, fluorine, hydrogen, and oxygen and nitrogen. Okay, it's Brinkelhoff is BRINCLHOF, and remember that they are the diatomic. So when they're by themselves, they get a 2. Okay, just a little extra add in here. Main thing here, it's single replacement reaction will happen. Correct answer is iodine by itself with a 2 because it's a diatomic, and potassium now bonded to bromine. Now moving on to number 37, it says what would the products of the reaction be? On this one, again, the tricky part on this one is looking at water. Anytime we look at water in a single replacement reaction, which we know this is a single replacement reaction because we have an element plus a compound, and so it's going to produce an element plus a compound. And so when we're trying to figure this out, the main thing we have to think of water is hydrogen bonded to hydroxide. So we need to think of water as this. Now what we need to see is that we have to look on our activity series, because this magnesium is a metal, and that hydrogen in the very front is acting as a metal. And what magnesium is going to try to do is magnesium is going to try to replace that hydrogen. And we look on our formula chart and we see that magnesium on the activity series is higher than hydrogen. So magnesium is going to replace that hydrogen. So what's going to happen is we're going to have hydrogen by itself, and we're going to put a 2 with it because hydrogen is a part of Brinkelhoff. It's a diatomic. And now we have magnesium bonded to hydroxide, which all we do is just a simple crisscross. Magnesium is going to be plus 2, hydroxide's -1. Remember, our polyatomics are on our formula chart. We crisscross these guys and we get MgOH2, which we look and we see that it really doesn't matter what comes first, if it's MgOH2 and then the hydrogen, but we know that we see it right here. So number 1 would be our correct answer. Okay, on number 39 it says, which of the following series of metals is currently ranked in order of increasing activity? So when we're looking at this, anytime we're looking at the activity series, the top of it is going to be the most active, and the bottom is going to be the least. Okay, so the greatest activity will be at the very top of the activity series. And remember, this is on your formula chart. It's given to you. And what we will see is that on our activity series, lithium is the greatest. And if we keep on moving down, it'll go lithium, and then sodium, and then zinc, and then gold. Because lithium is the highest, and then it goes all the way down to gold, which is the least active. So the correct answer should be number 2. Okay, number 41, it says, which of the following metals is most likely to displace magnesium from one of its compounds? Now, if something replaces it, that means that it's more highly active than it. So basically what we're looking at is on the activity series, anything that is above magnesium is most likely to displace it. And the higher it is on the activity series, the easier it is to displace it. So when we're looking on our activity series, we see that the correct answer should be calcium, because calcium is the highest above magnesium on the activity series. And remember, that's on your formula chart.